Okay, now we're in Physical Chemistry, Chapter 18, Section 12. We're going to talk about a one-dimensional harmonic oscillator. First, we're going to look at that point of classical mechanics. So let's say we have a mass hanging by a spring from something that's stationary. We're going to call this our X position. So F is going to be the spring force, and that's going to be equal to minus K times X. That's Hooke's law. K is just property of the spring. So the minus sign is because the force goes up as displacement goes down. So X is the amount by which the spring is stretched, positive or compressed, negative. So at equilibrium, we'll say our X position is equal to 0. And of course we're using capital V for potential energy. And then the K is the spring constant. So this is like a force constant for atoms. So it measures the stiffness of the spring, or bond in the case of the force constant for atoms. So we have F, force, is equal to minus the derivative of potential energy with respect to X. And that's equal to minus K times X. So we're going to solve for dV. So we get the differential of the potential energy is equal to Kx dx. Now we can integrate that. So we get the integral of Kx dx is equal to V, and that's equal to 1/2 Kx squared plus C, where C is some integration constant. Now, potential energy is actually arbitrary. There's no actual, potential energy is equal to 0 reference. So we can just say that C is equal to 0 to make life easier. So if the potential energy is equal to 1/2 Kx squared. So for spring, that's classical mechanics, though. So this is a parabolic curve here. So we have the X position on the horizontal axis. It goes as far as minus A to the left and positive A to the right. And then it shows vertical axes against that. So when you're at equilibrium, the potential energy is 0. The farther you get from equilibrium, the potential energy goes higher. And then when you're at its farthest, plus or minus A, potential energy is at a maximum here. And again, potential energy is equal to 1/2 Kx squared. Now again, classically, we can't go beyond plus or minus A. We just don't have enough energy in the system to do it. Now Newton's second law is that F is equal to mass times acceleration, or mass times the second derivative of X with respect to time. And F is also equal to minus Kx by Hooke's law, for the spring example. So we get mass times the second derivative of X with respect to time is equal to minus Kx. Now this is a differential equation. We can move the mass over, so we get the second derivative of X with respect to time is equal to minus K over M times X. So what we need is some sort of a function X to match that. Function of X, should probably say. I'll say that. Function of X to match that. So this is an eigenfunction eigenvalue problem. So the solution is going to be X is equal to A sine of the square root of K over M times T plus B, where A and B are constants. A is the amplitude. Tau is going to be the period of oscillation. A and B are both integration constants. So we get minus A is less than or equal to X, which is less than or equal to positive A. So here's the sine wave. So if we have it going from 0 to plus pi over 2 pi, well this is the x-axis, right? So 2 pi of one oscillation, that's one period, that's tau. Not to be confused with tau for all space, of course. We have to keep reusing the same letters because there's only so many letters. So we have the square root of K over M times tau is equal to 2 pi. So we get tau is equal to 2 pi times the square root of M over K. And frequency nu is equal to 1 over tau, and that's equal to 1 over 2 pi times the square root of K over M. This is called the natural frequency. You'll notice it's independent of X, and it depends on the strengths of the spring and the mass. Of course, we're still talking about classical physics here. So we get the total energy is equal to the kinetic energy plus the potential energy. See, we switched from using V for potential energy, now we're using PE for potential energy. So you'll have to get used to that. Sometimes different books do it different ways. So we have kinetic energy is equal to 1/2 mv squared, and potential energy is equal to 1/2 kx squared. Now we have x is equal to a sine square root of k over m times t plus b, and we have the total energy is going to be equal to 1/2 mv squared plus 1/2 kx squared. Now remember, dx by dt, all this squared, this is the square of the first derivative, not the second derivative. Notice the parentheses. Order of operations matters. So dx by dt, the derivative of x with respect to t, is equal to the square root of k over m times a times the cosine square root of k over m times t plus b. So the second derivative of x with respect to t is equal to k over m times a squared times cosine squared times the square root of k over m times t plus b. Remember, v in this case is, lowercase v is velocity. So we have the velocity of x squared is equal to the second derivative of x with the first derivative of x with respect to t squared. Now we have the total energy then is equal to 1/2 mass times k over m a squared cosine squared times k over m square root of k over m times t plus b plus 1/2 ka squared sine squared times the square root of k over m times t plus b. So we're going to factor this out. We get energy total is equal to 1/2 ka squared times cosine squared times the square root of k over m times t plus b is equal to sine squared times the square root of k over m times t plus b. Now remember, from trigonometry, sine squared of alpha plus cosine squared of alpha is equal to 1. So these whole terms here, the reason we factored it out is you can see cosine squared plus sine squared is equal to 1. So we ended up with just the energy total is 1/2 ka squared by classical mechanics, Newton mechanics. And the energy, of course, of the system can be greater than or equal to 0. Now let's talk about something similar, but from the perspective of quantum mechanics. Now, potential energy is going to be the same as classical mechanics. We have potential energy, now as we're using V, is at 1/2 kx squared. So V is equal to PE is equal to potential energy. We use them interchangeably, just whatever makes sense. We're going to have to use Schrodinger's equation. So we get minus h bar squared over 2m times the second derivative of psi with respect to x. That's lowercase psi, remember, so that's the time independent. Plus 1/2 kx squared times psi is equal to energy of psi times psi. So this is a little harder to solve than a particle in a box. We have to use something called a harmonic polynomial. So the solution, it requires power series and recursion. But the solution is the allowed energy levels. So the solution is called energy of V is equal to V plus 1/2 h nu, where nu is the frequency of the oscillation, V is the vibrational quantum number, so unfortunately no is not velocity. So V, it can be 0 or 1 or 2 or 3 or 4, etc. So this is not a particle in a box. This is a little different. So V equals 0 is allowed. But it does show, again, that vibrational energy is quantized. So we have energy at level 0 is 1/2 h nu, energy level 1 is 3/2 h nu, energy level 3 is 5/2 h nu, energy level 3 is 7/2 h nu, etc. Now one thing that's interesting though, they're equally spaced. So we have the ground state where V equals 0, and that's energy equals 1/2 h nu. Next excited state is V equals 1, so energy equals 3/2 h nu. Next excited state, V equals 2, so energy is equal to 5/2 h nu, etc. You can see they're equally spaced out. But it also shows that the 0 point energy, again, just like particle in the box, is not equal to 0. And then as temperature approaches 0, then the energy approaches the ground state. Okay, so for V equals 0, psi of 0 is equal to alpha over pi to the 1/4 power, so that's the 4th root, times e to the minus alpha x squared over 2. So alpha here is 2 pi nu m over h bar. H bar, remember, of course, is h over 2 pi. And nu is frequency. Okay, so for V equals 1, we get psi is equal to 4 alpha cubed over pi to the 1/4 power times x times e to the minus alpha x squared over 2. And then for V equals 2, we get psi of 2 is equal to alpha over 4 pi to the 1/4 power times 2 alpha x squared minus 1 times e to the minus alpha x squared over 2. So this is what they look like here. So for vibrational quantum number 0, we get psi of state 0. It looks kind of like a bell curve. There's no nodes except for plus or minus infinity. And then for V equals 1, we get psi state 1, so we get a node, one node, and you can see it's at x equals 0. And then for V equals 2, we get psi 2, we get 2 nodes. And then for V equals 3, we get 3 nodes, etc. So here's a graph showing like energy levels here. So it can go from plus or minus A, and it's allowed to be in here, and then beyond plus or minus A is classically forbidden. Now there is a small probability that the particle is in the forbidden region. So tunneling is when what we call penetration into the classically forbidden region. The piezoelectric crystal expands or contracts with voltage, like sound makes voltage. Tunneling is a quantum phenomenon. There is no equivalent in classical physics. Now let's talk about radioactive decay. An alpha particle emission, same symbol alpha, but this is different from the number alpha we saw in the previous page. So this is an example of tunneling. Here's our H. So we have 0 to 8 million electron volts. So this is the energy barrier. Now the alpha particle, it only has 4 million electron volts. So to get out of the nucleus, the alpha particle should have more than or equal to the barrier energy. See, this is the 8 million electron volt barrier energy to get out of the nucleus. Now this doesn't violate conservation of energy. So this is like if you have a brick wall falling down and then somehow it just lands gently instead of falling hard. So see the scanning tunneling electron microscope handout. So hydrogen atoms can tunnel too. And electrons also leak due to tunneling. Now STM is a scanning tunneling microscope because protons can tunnel. And the STM is important to analyze surfaces because electrons tunnel from the tip to the surface.